Okay, let us consider a matrix group. Say G. Let us consider matrix Lie group G, which is continuously connected to the identity. So for example, SO3, rather than O3. Okay, so if we consider such a Lie group, so any element of G can be written as e to the power I alpha I xi. Okay. Where alpha I, are the dimension of G real parameters, and xi are the dimension G generators. Okay, we have shown this before. Now, by the group closure property, by the closure property of the group, what we can do is that we can say that E alpha xi times E I beta jxj, if you multiply two group elements, then I should get another group element, which I'm writing at e to the power I gamma k xk. Okay, so let me make a comment about this parameterization. Because previously we wrote G as e to the power I, e to the power alpha ixi, right? The I was missing, but here we're introducing an I. So by doing that, what we're doing is that we are switching from the mathematics convention to the physics convention. In both cases, the parameters alpha are real. But for mathematicians, they don't have this factor of I, because for mathematicians, group is a very abstract thing. Where would an I come from? But for physicists, we tend to think of these things as matrices. So, for example, for SU2, introducing an I here means that this guy becomes a Hermitian operator, Hermitian generator. So, here we are using the physicist convention, and the closure property is telling us this is the case. So, if our group G is abelian, then it's not hard to show that gamma of k is alpha k plus beta k. Okay? Or I should say, yeah. But most Lie groups are non-abelian. So this is not going to be useful. So what happens for general non-abelian Lie groups? Okay. So in that case, gamma is not going to have this form. So let's take this relationship. This is important, so let me write it over here again. So for non-abelian, let us expand this relationship in small alpha, beta, and gamma. Obviously, gamma I, it is going to be a function of alpha and beta, these parameters, right? So now if I look at equation star and take its log, then we can write this as gamma k x of I gamma k x of k. It's equals to log of e to the power I alpha I xi times e to the power I beta j xj. Okay. Now, for small x, if I take, we know that for small x, log of 1 plus x can be expanded to x minus x squared by 2, and then higher order. So this is the linear order, and this is the quadratic order. So we are going to expand this to the quadratic order because up to linear order, we only get this guy. And this guy is not going to capture the non-abelian nature of our group. So we have to at least expand to quadratic order. So if I use this formula over here, then I can identify x to be e to the power I alpha I xi, e to the power I beta j xj minus 1. And so now if you do a little bit of algebra, you can show, and I'm going to leave that as an exercise, that this x minus x squared by 2, that's going to correspond to I times alpha I xi plus beta I xi minus, there's no I, but a half, alpha I xi, comma, beta j xj commutator. Okay, so this is just a few lines of algebra, but it's worth doing. Okay, so this means that up to second order, we can write e to the power I alpha I xi, e to the power I beta j xj approximately equal to e to the power I alpha I xi plus beta I xi plus, let me make some room, plus half commutator alpha I xi, comma, beta j x j. Okay. But by the group closure property, this should be linear in X. That this should be e to the power I gamma of k times x of k. So this will only be true if the commutator for some gamma of k, which is a function of alpha and beta, x of I comma x of j is a linear combination of x of k, right? By the group closure property, this must be the case. And this relationship between the generators of a Lie group is called a Lie algebra. Okay, this is known as the Lie algebra G tilde of the Lie group big G. Okay, so this is let's call this equation star. So I think I'm going to stop here and take the attendance and take some questions, okay? So I'm sure you're full of questions, but just hang on a bit. I'm just going to take the attendance. So let's take some questions. You guys are free to go. Those of you who don't want to stick around, but I'm here for questions.
Sir, what is F?
What is F? Where?
Fijk in the
Oh
red
yeah,
box.
these are linear. These, okay, they are called, so f of I j k, they are known as structure constants. And so for example, if all the f of I j k's are 0, then we have an abelian group, right?
Yeah.
So they are essentially telling you how the generators interact around the identity element. In some sense, they contain the seed of group multiplication table for the Lie group. Okay, so yeah, they're called structure constants. So the comment that I wanted to make, of course, I will repeat this next time, is that the Lie algebra captures the non-commutative nature of the group around the identity. Okay. So the Lie algebra, captures the non-commutative nature of the group, or even the around the identity. So if the Lie algebra is trivial, if all the structure constants are 0, then that means the Lie algebra is actually commutative. It's nothing very interesting, right? Because we can always have a Lie group which is a bunch of factors of U1, right? So the Lie algebra of such a group would be trivial. All the structure constants would be 0. But we saw that for interesting groups like SU2, the structure constant I, j, and k, Fi, j, and k, they can be chosen to be the Levi-Civita symbol. Similarly for SO3. Okay, any more questions?
I have another question. So, we ended the series, or we truncated the series at this quadratic term, but is there any justification for that?
Yeah, I mean, you can go higher order, but the quadratic term is the one, you know, we just showed that the Lie, this is a very good question. What we showed is that this bracket, Lie bracket, forms a closed algebra. So, you know, what comes after the cubic term and everything, we don't need to go there to close the algebra. We can generate those cubic terms by, you know, taking more and more terms, but as far as the non-commutative, the leading order non-commutative nature of the algebra is concerned, you know, this suffices. So you might say, I mean, this is a very good question. There's a lot to unpack here. You might say, okay, but what happens when we have like three Lie, you know, generators multiplying, right? Stuff like that. So, you know, yeah, that's a very good question, and we will come to that in the next. I'll give you a way of thinking about it in the next lecture. Okay. So, for example, you know, the BCH formula that you showed in one of the tutorials, you know, you will get stuff like that if you consider, say, let me just use some general Lie. So suppose that X and Y and Z, these are general elements of the Lie algebra. Then you can consider, you know, stuff like that. So there's a way to deal with this, and we shall see how, you know, I mean, you can see how it's done, right? Because we can first write this as some F, Y, Z, say tau times t, or no, not y z t, right? And then we can write this as f of y z, x of t, and then we can say f of y z, f of x of t, and then some other Lie algebra s. So we don't actually need to know more. But I don't know if it's if that answers your question, say.
Actually, what I was wondering is that, like, could the third order term like unclose the algebra, like it would add something that couldn't be taken into account or something like that?
I don't think so, but you know, that's because I've never seen that. Maybe there would be a way to prove that using the BCH formula.
Okay, all right.